Alright, I am now going to replace the 100 kilo ohm resistor right here with a 47 kilo ohm resistor, and I put the 47 kilo ohm resistor on a meter. You can see it's 46.5 kilo ohms, so I know it's pretty close to what it's supposed to be. I'm going to pop it in where the 100 kilo ohm resistor had been. What do you think the new time constant should be? You know what the old one was. What should the new one be? Predict it. I'm going to make a measurement. We're going to see if your prediction is correct. Okay, I'm going to start it at 10 volts. There we go. I'll press collect. And we'll see exponential decay as soon as I flip the switch to the other side. There we go. And once it crosses 3.7 volts, and I'm sure it has, I can go ahead and stop this. And then we can measure the time it took to go from 10 volts. It started at 10 volts at 5.2 seconds. That's when it first started to drop. So I'll take 5.2 seconds as my starting time. And I'll find 3.7 volts or something as close as I can find to it. Right about here, 10.4 seconds. So it went from 5.2 seconds to 10.4 seconds. Take the difference between those two times. That should be your time constant. Alright, for this next phase, I'm going to pull out this resistor, the 47 kilo ohm resistor, and I'm going to put an unknown resistor in there. It's been covered, so I can't see its bands, so I don't know its value. Of course, I could measure it with the meter, but we'll do that after. Let's see if we can predict what its value is based upon the time constant that the combination of the 100 microfarad capacitor and this resistor exhibits. So I'm going to do the same thing that I had been doing. I'm going to start off, make this go up to 10 volts, go into Logger Pro. Here's my 10 volts. I'm going to press collect, and I'm going to flip the switch. There it goes. Exponential decay. Looks like it's decaying a little bit more slowly than the one that I just did, which makes me think that this resistor might be of higher value than the one that I had just used. Let's see. Alright, I was at 10 volts at 5.7 seconds. I didn't flip it till 5.7 seconds. And it went to 3.7 volts at 14.6 seconds. So the difference between 14.6 seconds and 5.7 seconds is your time constant. Use that to calculate the value of what you think the resistance will be. And I'm going to give you the measurement of the resistor right here. I'll attach it to my meter. Here's my meter. And let's see if you can predict what I'm going to measure right now. What does my meter say? My meter says 81.9 kilo ohms. So that's your known value. The one you calculate is your measured value. You can do a percentage error now. Alright, for this next part of the lab, I'm supposed to put in an unknown capacitor. So I'm going to put that in. I pulled out the other capacitor, and here goes this one. I'm going to put this one in here. And I'm going to put in a known resistor, and I chose to use a 100 kilo ohm resistor, actually 99.1 kilo ohm resistor, close to 100 kilo ohms. But that's the known value of resistance. So I'm going to put that in where the other resistor had been. Alright, so those are in. I'm going to set up my Logger Pro voltage Whoops, that's not the one I want to set up. I'm going to set up this one. Now I'm going to measure the voltage across the capacitor when I flip the switch. It should be 10 volts. There it goes, 10 volts. And then I'm going to press collect. Okay, here it goes. Flip the switch. All right, it's gone past. So let's see here. I don't like that little bump there. It's not very clean with this capacitor. But in any case, I'm going to say that it started at 4.7 seconds at 10 volts. And then at what time did it get to 3.7 volts? Let's see. I'll go with 9.5 seconds. So we have 4.7 seconds to 9.5 seconds. 4.7 to 9.5. Take the difference between those two, and that should be our time constant. From that, see if you can figure out what the unknown capacitance is. And I'll measure it for you. You can see it on the capacitance meter, so then you can actually compare it. It says 47 microfarads, by the way. Let's see how close it is to that, so you can get your percentage error. Takes a minute to get to it. Oh, not bad. 46.5 microfarads. Okay, it's supposed to be 47. It's like 46.6, something like that. Pretty good capacitor. See if that's what you get with a time constant. Okay, this last experiment is kind of interesting. What I'm going to do is I'm actually going to pull out the resistor. You may be asking, why am I going to do that? Because without a resistor, how can you have an RC time constant? But the actual meter itself, whether it's this meter or the meter that comes with the vernier system, this one, it has a resistance. It has a resistance, and it can't not have a resistance. It's a big resistance. It's so big that it seems so much bigger than the other resistor that when you put it in parallel, you don't really notice it. But I want to see if there's any way I can try to measure that resistance. I'm going to do it maybe two ways. The first way I'm going to do it is I'm literally just going to put the capacitor in the circuit and the voltmeter, and we're going to see if we have any decay at all and see if we can measure what that time constant would be. If I can get this to attach to that, that would be great. There. And here, so I'm effectively attached to the capacitor there. So now the meter itself, or the Logger Pro, is the resistor. And let's see if that actually makes a difference if it actually causes a time constant to appear when I flip the switch without any physical resistor you can see there, just the voltmeter or the Logger Pro itself hooked up to the capacitor. So I'm going to go to vernier here. I'm going to press collect. It should start at 10 volts. And then when I flip the switch, we should see it decay, but it's going to decay pretty slowly. Why is it decaying so slowly? Well, first of all, why is it decaying at all? And the reason is, again, is because the vernier system itself is a resistor. It's decaying slowly because it's a big resistor, so it's taking a while for the charge to flow out of the capacitor through the vernier system and come back here, because it's such a big resistor. That's why the time constant is so lengthy. Unfortunately, I ran out of time. I'm going to redo it, but I'm going to make it go for longer. Didn't have enough time to actually see it go down to 3.7 volts, which is what I'd like. I could actually find it from the value I have here, but it's a little bit more work, as you'll see in class. So I'm a little bit lazy. I want to go to 3.7 volts. So I'm going to extend the time I'm going to make the experiment go to, see, I'll make it go to a minute. 30 seconds just isn't long enough, so I'll go 60 seconds. I hope that's long enough. Alright, so I'll press collect, and it's going to start at 10 volts, and I'm going to drop it now. Whoops. Stop that. I don't know what happened there. Oh, what happened was this thing unsnapped. Just unsnapped again. I'll do it this way. I'll attach it to that wire. Hope that's better. Okay, so it's still physically attached to the capacitor, just at a different place. Looks like it is. It's measuring 10 volts. Press collect. Here it goes. Flip the switch, and down it goes. Now I have a whole minute to wait to see whether it'll go to 3.7 volts in that time. I think it will. And then from that we can figure out what is the effective resistance of the meter. It's going to be big. It's going to be big. It's going to be a lot bigger than any of the resistors we've used so far. And let's see where I'm at here. Passing 30 seconds. Similar to where it stopped before. It's going to 40 seconds. Come on, I got to get to 3.7 volts before 60 seconds, or else I'm going to have to redo it with a longer time. We're getting there. There we go. 3.7 volts. Alright, it passed it. So I can press stop, and we can see how long it took. So it looks like it started at 2.3 seconds when I flipped the switch. And let's see how long it took to get to 3.7 volts. 3.7 volts. Oh, long time. Long time. Wow, look at that. 3.700. I don't know if I can get much better than that. I'll go with that. So 46.2 seconds is how long it took. I'm sorry, 46.2 seconds is the time at which it reached 3.7 volts. But from that, you're going to have to subtract the time I started it, which is 2.3 seconds. I'll let you do the work. The capacitor I used here was a known value. The 47 microfarad capacitor was really close to 47 microfarads. So from that, estimate what the value of the input resistance of the meter is. You can't really do a percentage error because I don't have an independent measurement of that. Although maybe I do. I could do this. What I'm going to do is I'm actually going to hook it up to this meter, and you can compare your time constant value to the value I get by literally just hooking this up to the voltmeter. I'll put it right here so you can see it. I want to make sure you can see it. I'm measuring the resistance of the voltmeter, which may seem weird. Or, I'm sorry, the resistance of the vernier meter. It looks like about 1.07 mega ohms. See how close you get to it. And this was the last part of the lab, so I hope it made sense to you. Of course, ask me any questions if you have any. Take care. Good luck writing it up.